Welcome back to the deep dive. If you're working in finance, climate modeling, healthcare, really any of those fields, you know that accurate time series forecasting isn't just a nice to have. It's pretty much the core engine for making decisions. But you also know the headache that comes with it. You're always trying to capture these huge long-term trends right alongside, that really noisy short-term volatility.
And that is the universal challenge in temporal modeling. I mean, the paper we're looking at today really frames it well. The complexity is that real-world signals are just inherently multi-scale. You've got these coarse global trends happening over years, but then you have super fine-grained local noise and all these other complex structures moving at different speeds in between.
Right, and most models sort of force you to pick one. You either capture the big picture and lose the details, or you zoom in and lose the context.
Exactly, it's a trade-off.
And that inability to model everything at once is exactly the bottleneck this new work is trying to break. We're diving into a really fascinating paper today titled PRISM, a hierarchical multiscale approach for time series forecasting. It's submitted by Zihao Chen, Alexandre, Rudy Ma, Ian Knight, Sergey Shuvaev, and Eva Dyer.
And this team is proposing a genuinely new architectural approach. It's designed specifically to handle that multi-scale problem by structuring the signal's representation hierarchically, and that just means letting features be extracted and combined based on their resolution. They're claiming they can get better performance while keeping the whole thing efficient.
So their solution, PRISM, is designed to solve this and get state-of-the-art results. For our audience, this deep dive is a shortcut to understanding how a change in architecture can really improve sequence modeling. Okay, let's unpack this and get into how PRISM actually functions. Let's start with a name. It's a great acronym. PRISM. It stands for Partition Representation for Iterative Sequence Modeling. So when you hear partitioned representation, what's the core idea there that makes it different from, say, a big transformer or a deep wavenet?
The representation method is really the radical part. The main innovation in PRISM is that it tackles that multi-scale challenge with a learnable tree-based partitioning of the signal.
Okay, learnable tree.
Yeah, so instead of using a fixed size window or some kind of rigid downsampling, the model actually learns how to break up the signal to pull out features at just the right level of granularity.
That learnable part feels like the most important piece, right? It's not imposing a structure, it's finding one.
Precisely. And if we, connect this to the bigger picture of sequence modeling, what's so fascinating is the trade-off it's trying to solve. With traditional models, if you want global context, you usually have to blow up the receptive field, and that often leads to quadratic complexity and attention, which is just a huge burden on memory and compute.
Yeah, we've all been there.
But if you keep the model light, you risk losing those long-term dependencies, or you just smooth over important local changes. PRISM is built from the ground up to capture both the global structure and the local dynamics at the same time by basically keeping them separate but connected in this hierarchy.
Okay, but let me push back on that a little. The idea of multi-resolution analysis, that's not new. I mean, classical signal processing has used things like wavelets for decades to break down signals by scale. What stops PRISM from just being a more complicated, maybe less interpretable neural network version of that?
That's a great question, and it's a really crucial distinction for, an expert audience. The novelty is in the learnable partitioning. Classical methods, they impose these predetermined frequency bands or time windows. They're fixed. In PRISM, the model optimizes the partitioning itself. It learns where to split the time series and how localized that view needs to be to capture meaningful features. And this is especially useful in, say, non-stationary multivariate series, where the important scale might actually shift over time.
I see. So the tree structure itself is dynamic. It's optimized during training. That gives it a flexibility that, like you said, a fixed filter bank just doesn't have. This sounds like it's tailor-made for managing that high-dimensional, often messy data you get in multivariate time series, but without needing a model with a billion parameters.
Absolutely. It manages the complexity through its organization, which makes it really suitable for practical use cases where efficiency and adaptability matter a lot.
Okay, so if that's the blueprint, let's talk mechanics. How does this learned tree actually segment the data and pull out features? Let's walk through it, maybe starting at the highest level.
Okay, so we start at the root of the tree. The root is the anchor. Its whole job is to capture the global representation, the really coarse trends of the entire signal. You can think of it as summarizing the macro behavior.
Yeah.
The long-term drift, the lowest frequency parts of the sequence. It provides that essential context.
And if you've ever dealt with something like data drift in sensor logs or sudden regime shifts in market data, You immediately see why having that global root is so important. It stops the model from making local decisions that completely contradict the bigger picture. So how does it get from that big summary down to the fine-grained details?
It does that through recursive splits. So moving down from the root, the time series gets partitioned over and over, which generates these increasingly localized views. Each split creates a smaller, more focused time window. And the crucial part is that these splits are optimized based on the data itself. The paper implies this is done by optimizing some kind of differentiable splitting criteria at each node, which lets the model figure out the best way to chop up the data for the next stage of analysis.
Right, that's the technical core of it. The decision of when and where to partition the signal is actually learned. So once we get to a specific node in the tree, a localized segment, how are the features for that particular scale actually extracted?
At each node, that segment of data is projected onto a time frequency basis. This is the dedicated feature extraction layer for that specific scale, and this choice is very deliberate. It's borrowing from the efficiency of classical signal processing. The authors give some specific examples of bases you could use here, like wavelets or exponential moving averages, EMAs.
And why do that? Why lean on classic methods like wavelets and EMAs instead of just sticking a fully dense neural network at every single node? Is that part of the lightweight claim?
Exactly. It's all about efficiency. Using these established bases lets the model very efficiently capture scale-specific features, things like cyclical patterns, sudden shocks, momentum changes, that are only relevant to that specific window. And it does it without the massive computational overhead of deep, dense layers. You're basically leveraging decades of signal processing knowledge inside a modern learnable architecture. So you could have a global EMA trend being extracted at the root, and at the same time, highly detailed wavelet coefficients way down in the branches.
Okay, so we've got scale-specific features being generated at every level, from the macro trends at the top to the micro fluctuations at the bottom. The next big challenge is obviously integrating all of that information for the final prediction. This brings us to that final step, the aggregation across the hierarchy. How does PRISM fuse this whole multi-resolution stack together without losing the signal from any single scale?
The aggregation is fundamental to making this work. It's what resolves the whole representation problem. The paper suggests this aggregation fuses the global trends from the root with all those specific localized features from the branches. For anyone technical, this isn't just simple concatenation. It's probably something like a weighted combination or an attention mechanism that learns how important each scale's representation is when it's calculating the final feature map for the forecast. This kind of systematic fusion ensures the model gets a representation that is context-aware, temporally localized, and structurally complete all at once.
That structural completeness is really the key differentiator. It avoids that problem where you lose the global context.
Yeah.
Okay, now here's where it gets really interesting. What are the actual performance claims the authors are making based on this architecture?
The experimental results are pretty robust. The paper reports that PRISM consistently and significantly outperforms current state-of-the-art methods for forecasting, and this is across standard benchmark datasets. So the implication is that this hierarchical partitioning approach just fundamentally provides a better structure for modeling these complex multiscale dynamics than other top models like LSTMs or mini transformer variants.
And where does it really shine? Because you often see models that are good at short-term prediction, but then just fall apart on long-horizon forecasts.
Well, PRISM's strength seems to be exactly where other architectures tend to struggle, long horizon forecasting. Because it explicitly holds onto that low-frequency global context at the root, the model can stabilize those long-term predictions. It avoids the kind of catastrophic drift you see when a purely local model tries to extrapolate too far into the future. So that architectural choice directly translates into a real performance benefit.
And we keep coming back to this idea of efficiency. The lightweight and flexible claim is a big deal, especially with the current trend of just building bigger and bigger models. How does PRISM get the performance without that huge parameter count?
It's a direct result of the design. That hierarchical tree structure is just inherently more sparse compared to the dense matrix multiplications and, the quadratic complexity of self-attention in a pure transformer. By using efficient, localized projections at the nodes instead of just stacking huge, dense neural layers everywhere, they've built a framework that gets its power from organization, not from sheer size. And that says a lot about its practical use, especially for deploying in places with limited resources that still need really high-fidelity predictions.
Lightweight, flexible, and outperforming the state of the art. That's the trifecta every data science team is looking for. And for any of you listeners already thinking about trying this out, the authors have made the code available, which is great. It allows for immediate validation and integration into existing workflows.
Yes, that openness is a really strong sign of their confidence in the method, and it really helps drive adoption of new thinking in the ML community.
Okay, that was a pretty thorough breakdown of PRISM, partition representation for iterative sequence modeling. Let's quickly nail down the key takeaways you can use in your own thinking about time series architecture.
I'd say the core strength is PRISM's learnable tree-based partitioning. It resolves that conflict between global context and local detail by dynamically learning the analysis path.
Right. And second, the feature extraction at each level is super efficient. It relies on projecting data onto established time frequency bases, like wavelets or EMAs, to get features that are only relevant to that specific scale.
And finally, it's the successful aggregation across the hierarchy. That weighted fusion of the global view with all the localized features is what provides that complete, robust representation. That's what allows the model to get these SOTA results, especially in complex, long-horizon forecasting.
So if you connect this to the bigger picture of architectural efficiency in machine learning, PRISM is really a compelling case for moving away from just stacking fixed blocks. It shows that a structurally intelligent model that learns its own representation can be much more powerful and efficient than just adding more dense layers or more attention heads.
It's a fantastic example of blending that classic signal processing intuition with modern optimization.
So what does this all mean for the future of forecasting? We've established that PRISM uses this dynamic learned tree. Now, compared to fixed predetermined multiscale methods, which often struggle with non-stationarity, what might the specific advantages be here, maybe in terms of interpretability or robustness to noise, when the very structure of your feature extraction is learned and adaptable? That's a critical question for you to think about as you maybe go and explore the implementation yourself.
An excellent thought to end on. The ability to actually look inside that learned structure could offer some really unique insights.
Thank you for joining us for this deep dive into PRISM. We hope this has given you the sophisticated foundational understanding you need to apply this exciting new development to your own work.